Hello, my name is Delaney Miller, and today I'm going to be discussing with you my research on the pH effects on the electrosynthesis of biomass-derived furanic compounds using redox mediators. I worked on this project with Emily Carroll and Dr. Shelley D. Minteer as a part of the University of Utah Chemistry Department. So first I would like to discuss with you the general reason why we chose to do this project, which is because of its utility in biomass upgrading. So sustainable feedstocks such as biomass have shown to be very promising for creating energy and bioplastics. So when we start with things such as corn or wheat or even lumber sometimes, we can get this converted to a sugar such as glucose or fructose, and then we can further get it to a furanic compound such as HMF, which we have shown right here. HMF is not the most stable molecule for industrial purposes, so we have chosen to start with BHMF right here for this electrosynthesis. So generally for this electrosynthesis, we have our substrate here, and we can complete this electrochemical oxidation by adding in our nitroxyl radical here. For this, it's either going to be 4-acetamitotempo, or 4-methoxytempo. And then through catalyst regeneration, organic catalysis, we can go around and eventually get to our product here, which is FDCA. So here we have some of these intermediate steps for this oxidation. Each time getting more things oxidated, going from this alcohol to aldehyde and so forth, getting us to our final product. So we did this using scan rate studies, which we used using cyclic voltammetry to assess reversibility and predict catalysis. Then we did substrate titrations, which we also used using cyclic voltammetry because it is non-destructive. And basically, if we show an increase in current, then we see that our substrate is being converted using catalysis. Finally, we did analysis using bulk electrolysis as well as ultra-high performance liquid chromatography and mass spec. And we did this at pH 9.2, and I will explain why in a second. So generally for our catalytic scheme, we start with our nitroxyl radical, which is one of these guys right here, and then we can electrochemically activate it to get to an oxoammonium cation. From there, our substrate can be added in, and then we get an alcohol adduct, and then it can be oxidized. And the cycle, hypothetically, will continue from this reduced form of tempo, and then be electrochemically regenerated back to the nitroxyl radical. And this happens primarily through basic conditions, as we can see over here, where we have this oxidative peak, where when we add our substrate, we see an increase in our current here, indicating that catalysis is occurring. And we see this for each one of these tempo molecules at pH 10, which is a basic pH. Whereas at pH 3, we are not seeing this as much. The addition of the substrate, which is 1 millimolar BHMF, is not indicating that we have catalysis shown. And we propose that in acidic conditions like the pH 3, this nitroxyl radical will likely form the reduced form tempo, which is electrochemically inactive, and will be unable to continue this cycle here in the catalytic scheme. Our further results have shown similarly at pH 9.2, where we are able to see catalysis occurring, as well as with our injection of BHMF. As our substrate concentration increases, we are able to see plateau and increase in current, indicating catalysis. Our bulk electrolysis also indicates that this electrosynthesis was able to be completed at 100% conversion, as we can see with our Faradaic efficiency on each one of these tempo molecules, as well as with our mass spectrometry results. Overall, we were able to complete this 8-electron transformation from BHMF to FDCA using our methods, and our methods of screening were very helpful in determining this. I would like to thank everyone who helped with this project, and also the Office of Undergraduate Research for continuing to fund this. Thank you so much.